Hey guys, today we're going to be talking a little bit about global climate and a lot about biomes, and this is chapter 4. So we'll just start by looking at a map that shows us the layout of all of the various different types of biomes that we have and that we'll learn about today. And what we're going to be talking about is that there's a predictable way for us to figure out where we see which types of biomes based on the annual average temperatures and precipitation. So we're going to start off talking about climate stuff and why those types of conditions exist in different places of the world, and then we'll eventually get to these different biomes, where they're located, and the different characteristics of each of them. So just to kind of take a first glance, you can see we've got a lot of tropical rainforest down here around the equator. We have a lot of deserts up here around 30 degrees north and 30 degrees south. Savannas are like your tropical grasslands. We have a lot of those in Africa and South America. We have a lot of your colder biomes up here at higher latitudes, like your tundras and your boreal forests. And then if we look over here at the U.S., the biome that we live in is a temperate deciduous forest, and we also have temperate grasslands that are in the Midwest of our country and over here in Eurasia. If you notice, we have a lot of temperate deciduous forests over here in Europe as well. And that about covers my brief little overview, but we'll get into the locations of each of them as we talk about each individual biome. Okay, so the first thing we need to know about climate and how it affects biome placement is what's the main initial thing that's going to drive our climate patterns, and that's going to be the way that the sun hits the planet. So this says that we have an unequal heating of the Earth, and that's due mostly to the shape of our planet. So it says, as the sun's energy passes through the atmosphere and it strikes different things like the land and the water, it's going to warm the surface of the Earth, but this warming does not occur evenly. It occurs unequally, and the reason for that, one of the main reasons, and I drew this little picture to try to demonstrate, I've got a better diagram on the next page. It says the variation in angle at which the sun's rays strike. So if you look at this drawing, this ugly red circle is supposed to be Earth, and then these blue lines are supposed to be solar radiation coming from the sun. And the point I was trying to make with this picture is that if this is the equator right here, this is right in the middle of the planet. This is right where the sun is going to be hitting. It's going to hit it perpendicular. It's going to hit it right at a right angle. It's going to be direct rays. But then if we go to higher latitudes, like up here in the polar north or in the south, it's hitting at more of a longer angle and more of a diagonal angle. So it's going to be way more concentrated here at the equator than it is when it hits at these higher latitudes. So that also pertains to the second point, the amount of surface area over which the sun's rays are distributed. And then the third point says some areas of Earth reflect more solar energy than others. That's called albedo or albedo. I've heard it pronounced both ways. That is the phenomenon, and I think we've mentioned this before earlier in the year, but that's the phenomenon where anything white in color or light colored is going to reflect sunlight. Anything dark in color is going to absorb, but yeah, your lighter colored things reflecting, that's called albedo. So polar regions that have a lot of white stuff like snow and ice are going to have more reflection. Okay, and so this is my better picture that illustrates that point that we have unequal heating of the Earth's surface. So again, we said the sun's going to hit right here at the equator at a right angle, at a perpendicular angle. So it's going to be very, very concentrated heat right here. So it says all within this area of 38 north to 38 south is where we're going to have that major heat gain. And then what we're getting ready to learn about is that heat, as it hits here in the middle of the planet, it's going to generate these convection cells of warm air masses that are going to move from the equator and move the warm air to higher latitudes. Okay, so, and just real quick, because we're talking about climate and we need to know what climate is. Climate is different from weather. Weather would be like your day-to-day conditions, like today it's overcast and rainy, and then tomorrow it'll be sunny and warm. That's the weather, but climate, it says it's the average weather patterns for an area over a long period of time, and they define that as anywhere from 30 to a million years. What two things determine the climate of an area? Your two major things are average precipitation and average temperature. That's very important. Okay, so the precipitation and the temperature of an area will determine the climate. And what things influence those? That's going to be the latitude, which we'll talk about in a moment. Altitude is how high above sea level you are. So if you're up high in a mountain, you're at a high altitude. And then ocean currents are also going to carry heat from the equator out to the poles, in addition to your warm air masses. Okay, and then before we get into these convection currents, we need to know a little bit about just some properties of air. So one of our properties of air we need to understand is density and how that works. So it says less dense air rises, and that's going to be your warmer air is less dense, and your denser, colder air is going to sink. So that's a simple fact that we've known since we were little kids, that warm air rises, cold air sinks. This is why, because warm air is less dense and cold air is denser. Water vapor capacity. Warm air has a higher capacity for water vapor than cold air. And that's why, especially even in the area that we live, and then if you go down into the southeastern U.S., when it gets hot, it is humid. It's because that hot air can hold on to a lot of moisture. So that's why you see warm air having a lot of humidity. Adiabatic heating and cooling is a little bit of a weird concept. It says, as air rises in the atmosphere, its pressure decreases and the air expands. So you can imagine, these particles of air, as they're going upward, they're going to be able to expand. There's less pressure up there. That's actually going to cool it down. And then it says on the opposite hand, when air sinks, the pressure increases as we get closer to Earth, and as we get closer to Earth, the pressure increases and the air decreases in volume, which raises the temperature. You're kind of squeezing the air mass into a smaller amount of area. So higher pressure, less volume, and the air is going to be warmer. And then latent heat release is when water vapor in the atmosphere condenses into liquid water, and energy is released. So we know with evaporation, your water is going from liquid to vapor form, but then when it condenses in the atmosphere, it turns back into liquid in the cloud. So when that happens, you're going to be giving off a little bit of energy, which is actually giving off a little bit of heat. So it says the air will become warmer, and this warm air will rise. So these are going to be important concepts to understand with the convection currents. Okay, so what this picture is of, this is planet Earth, I've laid it on its side. There is the equator. We call this the intertropical convergence zone. This is where a lot of the heat is hitting, and this is where you have your converging of these two Hadley cells right here at the equator. So let me go ahead and walk you through these steps of how these convection currents form. So step 1, it says, as the ITCZ, the sun heats the moist tropical air, causing it to rise. So right where we said all that sun is coming in and hitting right at the equator, you get all that heat. You're going to have tons of evaporation, because we know that's how water evaporates. You add heat to it, it's going to evaporate the water, so you get lots of cloud formation. Step 2 says the rising air experiences that adiabatic cooling, which causes water vapor to condense into rain and fall back to Earth. So you have condensation, you have clouds form. When you have lots of clouds form in the atmosphere, you're going to get lots of rain. So lots of evaporation and then lots of clouds squeezing out their rain back down on the equator. So this is going to be one of the reasons we see all these rainforests right here, right around the equator. You get tons of warm temperatures and tons of rain. Then number 3, we're going to come up a little bit more, and it says the condensation of water vapor produces latent heat release. This causes the air to expand and rise further up into the atmosphere. So we've kind of squeezed out that air. Now it's gotten warmer, so it's going to keep rising, rising, rising. And then number 4 says, finally, that warm rising air displaces the cooler, drier air above it to the north and the south. So now that it's risen, it's going to start to have that cooling, and it's going to start to trickle back down. It's going to trickle back down right at about 30 north and 30 south. And that's what number 5 says. The cool, dry air, now that it's been squeezed out, we've kind of squeezed it out when we had all the precipitation, and it rose and it got colder. That cool, dry air now sinks back down to Earth. It experiences adiabatic heating, which we said is when it gets closer to Earth, the pressure increases and it warms up. So it says it's going to reach Earth's surface as warm, dry air, and then it's going to cycle back towards the equator again. So lots of sun right here at the equator is going to cause lots of evaporation, which causes lots of cloud formation, which causes tons of precipitation. And we squeeze all the precipitation out of the clouds. The air rises up, it's going to cool down. As it sinks back down, it's going to cool and be compressed by the adiabatic heating, and as it's compressed, it gets warm. So we get really hot, dry air at 30 north, 30 south. So we have another predictable biome that we find at 30 north and 30 south, and those are going to be your deserts. So we get a lot of your tropical rainforest right here at the equator, and 30 north and 30 south we get a lot of deserts. Okay, so this is just another picture showing the same thing. This is what we just looked at. We said right here at the equator, tons of sun causes all the evaporation, all the rain. There's your rainforest. Squeeze out those air masses. They sink back down at 30 north, 30 south in the form of cool, dry air, or warm. It gets warm as it does the adiabatic heating. So it actually becomes warm in a lot of cases. So deserts at 30 north, 30 south. Then I wanted to show you guys the other steps to these convection cells. So you have these currents converging here and here. They converge and you squeeze out the clouds, and then they fall. And you can see here they fall at 30 north, 30 north. This one falls at 30 south, 30 south. Let's go to 60 north. 60 north, again, we see the converging of these two masses, and they're both converging upward. So again, we're going to get a lot of that evaporation, condensation, tons of rain. So we're getting lots of rain, but the rain is happening at a high latitude of 60 degrees. That's way higher than where we live. I think our latitude is around 35 or 36 degrees north. So at 60 north, we're much higher. It's going to be more of your boreal forest or your evergreen coniferous forest. So we see a lot of those at 60 north and 60 south. I told you guys that we are in between the 30 and the 60, so we're right in here. We're a temperate deciduous forest, and they also stick grasslands in there as well. We're kind of in the middle of two of these big convection cells. And then again, if we come all the way up to 90 north and 90 south, you're going to have descending air masses again, and you can imagine you'd have another descending air mass over here. And that's going to be that dry air. And in this case, it's going to be definitely very cold, dry air, and that's where you're going to get your tundras, because tundras are very dry as well. So these are convection currents, and that's one of the major ways we can kind of predict what sort of biomes we'll see at different latitudes. And by the way, latitudes are your lines that run east and west, and a way that you can kind of remember this latitude versus longitude. We don't really talk about longitude that much in this class, not until we get to volcanoes and plate tectonics. But just think of the Jimmy Buffett song, Changes in Latitude, Changes in Attitude, which, you can think of, we're up here in temperate deciduous world, and maybe you'd like to be down here near the equator on a nice warm beach. So again, we're thinking of these horizontal lines getting to a lower latitude to be closer to the equator. Okay, so latitude are your side-to-side lines. Okay, so just a little bit more on those convection currents. I don't need to read that because we just talked about that. The specific ones we talked about right there in the middle at the equator, those are called Hadley cells. And it says they're the convection currents that cycle between the equator and 30 north, 30 south. At the equator, we're getting the tropical rainforest. At 30 north, 30 south, we're getting the deserts. The ITCZ is the area of Earth that receives the most intense sunlight, and where those branches of the Hadley cells converge. So I'll go back to that picture. It's right here where these two Hadley cells are converging. And the polar cells are the ones all the way at the very top that we just looked at, and it says these are the convection currents that are formed by air that rises at 60 north and 60 south and sinks at the poles 90 north, 90 south. And we said at 60 north, 60 south, you get your boreal forests, because wherever you have a lot of rain, you're typically going to see forests. 90 north, 90 south, we said you have the dry, cold air. That's where you see your tundras. Okay, and then the other major driver of climate issues besides these air masses and these convection cells would be your ocean currents. And so ocean currents, again, they're going to be mainly driven by the way that the Earth is heated, so the temperature, but they're also driven by things like gravity, winds, the Coriolis effect, which we'll talk about more later, and the location of continents. And it says here, warm water, like warm air, expands and rises. And then we've got this huge, large-scale pattern of water circulation all over the planet. I'll show you a couple pictures of that. We call those gyres. And it says the ocean surface currents rotate in a clockwise direction in the northern hemisphere and a counterclockwise direction in the southern hemisphere. So we'll talk more about ocean currents when we get to our water unit later. But let me show you some of these pictures. Let me show you the pictures of all the currents first, and then we'll go back and look at that last slide. So this is showing you, and you do not need to know all of these right now, especially for this unit. We'll talk about some major ones later on in the year. This just shows you, again, you're going to have most of your heat hitting right in here, right around the equator. So that's going to heat up the water, and that's going to kind of spin this warm water to then move to higher latitudes. So one of our major currents that we're going to learn about in this class is this North Atlantic current that comes up the eastern side of the U.S., and it moves warm water all the way over here to Western Europe. And an important thing about this is because of that current, it keeps Europeans over here at a relatively mild climate for the latitude they're located at. They're located at a pretty high latitude. So if you look at kind of where they are in comparison to the U.S., you would imagine that they would be really, really cold. But because they've got this really warm North Atlantic current that's constantly bringing warm water and warm air masses over to them, it keeps their climate relatively mild. So yeah, you've got warm stuff going from the equator upwards, and then of course you're going to have polar currents coming from your high latitudes, both north and south, that are coming into the equator as well. And I'll just come back and get this slide real quick. So this says thermohaline circulation is another oceanic circulation that derives the mixing of surface and deep water. So this is dealing with your different levels of the water, and you have mixing within those levels. And it says scientists believe this process is crucial for moving heat and nutrients around the globe, and the thermohaline circulation appears to be driven by surface waters that contain unusually large amounts of salt. So salt and the density of the water is going to be another big driver of these things. Something kind of important that we'll talk more about later are these upwelling zones. These upwelling zones are where you're going to have water moving from deep down and moving upward, and they're going to bring a lot of nutrients with them. And wherever you see these upwelling zones, you're typically going to have really good fish stocks and really good fishing areas. This is a picture of the thermohaline circulation we were talking about. Just kind of walks you through the steps here. It says that they started off with the warm water flowing from the Gulf of Mexico to the North Atlantic. So we talked about that North Atlantic current right here, where some of it will freeze and evaporate, and then it turns around. It says the remaining water, now saltier and denser, sinks to the bottom. So here's where we're dealing with your different depths or your different levels of the water. So that it's warm, it's on top at this point, and then once you have some evaporate, it's going to get colder, so it's going to sink down. So this is going to be a deep ocean current that's going down on the bottom of the ocean. Then you follow these cold, deep currents through here, and that's what number 3 is talking about. The cold water travels along the ocean floor, connecting all of the world's oceans at this point. And then, if we follow over here to number 4, the cold, deep water eventually rises back to the surface and circulates back to North America. As it picks up some heat, it'll get shallower here. Okay, so just know that both warm air masses and the way that the water is heated on the planet are going to drive the climate, and they're going to drive where we see different biomes. Okay, so let's talk about biomes now. We obviously know that climate affects where we're going to see different biomes, where we're going to see different species on the planet. And it says organisms possess distinct growth forms due to adaptations to local temperature and precipitation patterns. I definitely misspelled that, sorry. So all of the biomes we're going to talk about, you're going to have animals that are perfectly adapted to deal with the types of temperature and precipitation issues that they have there. And so that's what we actually define a biome as. It says the presence of similar plant growth forms in areas possessing similar temperature and precipitation patterns. And they don't really ever use animals in the definition. They're mostly concerned with the similar types of plant life that they have in certain regions of the world that have temperature and precipitation patterns. Okay, and then here's just a graph where we can see some of your different biomes and what types of precipitation and temperature would yield these different biomes. So at the high end of this graph, we see that if you have high annual precipitation and high temperatures, you're going to end up with a tropical rainforest. If we come down here and you look at, okay, what if we have high temperature but low precipitation? That's going to yield something like a desert. And then in between those two things, you could get like a savanna, which is your tropical grasslands, like Lion King biome is what I call that one. Yeah, and then in the middle, if you're kind of in the middle, we have a lot of your forests. Typically, wherever you have a lot of rain, you're going to have forests because you need a lot of rain to sustain large plants like trees. And then down here at the kind of the little point down here where we have very little precipitation and low temperatures, you're going to have your cold, dry tundra. Okay, and we've already looked at a map like this earlier, so I'm just going to kind of roll through that right now. If you want to spend some more time on that, you can kind of rewind or just look at my PowerPoint. Okay, so let's talk about tundra. I'll do a couple of the biomes on this first video, and then I'll save the rest of them for a part 2 video. So we'll start with the tundra. We just said it's going to be cold and dry. It's typically treeless, and you're just going to have very low growing vegetation, which means like little small plants that are close to the ground. In winter, the soil is completely frozen. It's called permafrost. It's going to have a very short growing season, meaning that there's only a short amount of time where you'll see plants growing. It's usually only for about 4 months during the summer. And in their summers, you have really long days and really short nights because they're at such a high latitude. It's actually really cool. You guys are going to get tired of hearing me talk about Iceland, but that was one of my favorite places I've ever been. But we went there in August, and the days were really long. Even in early August, the sun didn't set until like 11 p.m. I don't think, and even when it did, it was kind of this weird hazy looking thing. But yeah, summer they have really long days and really short nights, and then the opposite occurs in winter. They have really long nights and really short days because of where they're located on the planet. And then again, most importantly, they have a very short growing season during this short summer. Underlying soil, we said it's known as permafrost. It is impermeable, and it's a permanently frozen layer that prevents water from draining and roots from penetrating. That's why you're not going to see very large plant life. Where do we see most of our tundras? We find them in northern regions of Russia, Canada, Scandinavia, which is like Norway and Denmark and Sweden and those kind of places, Alaska, Antarctica. And then you can also have what we call alpine tundras, which are just found like at the tops of mountains, and those could be found even at lower latitudes. Even in our country, we have alpine tundras that are up high in the mountains. So the types of plants that you would see in a tundra are going to be small woody shrubs, mosses, and heaths and lichens, stuff that's low to the ground and can easily grow on this rough terrain. So that's the type of plant life. Those are probably a lot of mosses and lichens. Here's where we find tundras on the planet. We see them at very high latitudes. So northern Eurasia, Greenland, there's little Iceland. A lot of northern North America. Over here we have Alaska, northern Canada. And then you'll notice a lot of these little blue lines here, those are representing alpine tundras that we would have at the tops of mountains. This diagram right here is called a climatogram. We're going to be working with those over the next couple days. The way that these work, well, you read the country information is up here. They're going to give you average precipitation, and your precipitation numbers over here, and the precipitation line is going to be the one in blue, and your average temperature is in red, and here's your temperature data over here. So we show very cold temperatures for most of the year, and then they finally get up a little past 0 degrees Celsius in the growing season, and you'll notice they highlight the growing season in gray down here. Their growing season is only going to be in June, July, August, and September, and it's going to be limited mostly by temperature but also by precipitation because it's relatively dry. We'll go ahead and do the boreal forest as well. This is going to be your pine tree forest, as I call it. They're forests that are made up primarily of coniferous or cone-bearing evergreen trees or pine trees that can tolerate cold winters and short growing seasons. These evergreen trees appear green all year, and they only drop a small fraction of their needles as needed. and that is due to them having a waxy covering on their needles. They're able to withstand the cold, harsh temperatures, so that's why they're called evergreens. Examples of these types of trees would be pine, spruce, fir, birch, maple, and aspens. If you do have some deciduous trees, which some of those I just listed are deciduous, and deciduous means that they lose their leaves in the fall to go dormant in the winter. It says deciduous trees do have to drop their leaves to go dormant in winter, while coniferous trees can tolerate the below freezing conditions, so they don't drop very many of their needles. They'll stay green all year. Boreal forests are usually found at pretty high latitudes, so up around 50 to 60 degrees north in Europe, Russia, and North America. It's called subarctic because it's below the tundra, but it's still going to have a very cold climate. The plant growth is going to be more constrained by temperature than precipitation. So if they're right at 60 north, we said that you do get a lot of precipitation there because that's where you have those convection cells converging and rising. So you do get a decent amount of precipitation, but the temperatures are cold, so temperature is going to be your main constraint on plant growth. The soil here is going to be nutrient poor due to slow decomposition rates. That is due to having really cold temperatures, and you've got all these waxy needles from plants that need to be broken down, and they are resistant to decomposing. So you don't have a lot of good fast decomposition, which means you're not going to get a whole lot of nutrients into the soil. These are bad biomes to use for agriculture because they're not all that great for growing crops, but they're an important source for logging to get things like paper, pulp, and building materials. So one of our environmental issues of this biome is overlogging. And I'm going to go ahead and stop this video right now for part 1, and we'll pick up, actually let's get the diagram here, then I'll finish. So I just wanted to show you real quick the map of your boreal forest. We have them up here in northern North America and up here in northern Eurasia. Here's your climatogram. A decent amount of a growing season. You have, let's see, this is April, May, June, July, August, September, October. So you just don't have a growing season in the harsh winter. But yeah, it's subarctic because it's found right below the tundra, but still relatively high latitudes for this biome. And then there's a picture of what a boreal forest might look like. Okay, so now we'll go ahead and end part 1 of the video, and I'll continue the rest of the biomes on part 2.